Hello everyone, this is Professor Iris Miano giving you a Math 50 pre-statistics lecture on sections 10.1 and 10.2, which collectively span an enormous number of exponent properties, rules, examples. Basically, everything you need to know about exponents and exponential expressions is here in this video. So, definitely a lot of good information here, and we'll need to start by familiarizing ourselves with the rules. So here in each of these rows, we have a property name, the basic rule that's incomplete, and we're going to fill it in, and then we're going to put off to the side what the idea is behind this rule, which is hopefully going to help us remember the rules and to remember and understand truly when it's appropriate to use these rules. So recognize that we are letting m and n be just any counting numbers that are at the moment non-negative. We'll talk about negative exponents in 10.2. That's when that rule is going to come about. Okay, so, and they're just any numbers that you can think of, no fractions though, just yet, and no decimals. So think of the numbers like 1, 2, 3, 4, 5, those kinds of numbers. So if we have two exponential expressions, so that's b to the n power being an exponential expression where b is the base and n is the exponent, multiplied by another exponential expression, the second one being a base b also, but an exponent of m, then we can use the product property or the product rule for exponents. I often call it product rule, to simply add the exponents together in a single exponential expression of that collective base b, okay? So just add the exponents together. So the idea being when exponential expressions of the same base, so same base multiplied, means you add exponents. So we're going to try and come up with like little, one-liners to describe what's going on here in the idea column, all right? So quotient property, similarly but a little different, dictates that if you have exponential expressions being divided or, in a fraction configuration, as long as the bases are the same, you get to subtract the exponents, but make sure you do it always numerator exponent minus denominator exponent, okay? So same base divide means subtract exponents. This will be our one-liner idea. So same base divided means subtract exponents. Okay, now what if you have a product inside of a quantity, so inside of these parentheses here, and they're collectively raised to a power? Well, how do you simplify that? This is called power of a product rule, okay? They call it raising a product to a power, which I think is a little bit more wordy and unnecessary. But anyway, it's kind of like you get to distribute that exponent to each individual item inside of the parentheses here. So it is going to simplify to b to the n power c to the n power, okay? So it's the idea being that you distribute the exponent to all factors. Okay, so similarly, but now we're dealing with a quotient instead of a product inside of the quantity, you're going to distribute that n exponent to both of the factors in the quotient. So it'll be b to the n power over c to the n power. So distribute the exponent to all factors. Again, basically has the same idea, it's just you're dealing with a quotient inside instead of a product. Okay, now if you have an exponential expression raised to a further power, so by that I mean inside of some parentheses you have some exponential expression and then there's another exponent waiting in the wings outside, that's when you multiply the exponents together. So that's supposed to be a raised dot in between the m and the n. So I call this power of a power rule, or just power rule, okay? So this is power of a power multiply exponents. Oops, let me erase that real quick. And we're going to wrap things up in this set of rules by introducing the zero exponent rule, which is to say that it's equal to a 1, okay? So hopefully that's easy for us to remember. A little bit of an explanation as to why this might be. Consider the quotient rule in which you subtract the exponents, right? But let's say you had something where you knew what the exponents were. They weren't just some unknowns like m or n. And let's use the quotient rule, right? Which would dictate that you subtract the exponents and you get b to the 3 minus 3 power, which is b to the 0 power, which according to this rule has to be equal to 1. But wait, think about it as far as what you know about fun ones, which are fractions whose value is 1, but it has a fun representation because the numerator and denominator equal the same number. We would just say that this equals 1 by virtue of it being a fun one. Virtue, that's not how you spell virtue. Let's try that again. Of by, that's supposed to be Y right there. All kinds of sloppy with my handwriting. By virtue of being a fun one. So what's a fun one? A fun one is any fraction whose numerator and denominator value are equal to each other. It's something over itself, basically. So we'll just say anything raised to the 0 power is 1 as the idea. Equals 1. Okay, and you may notice that as you scroll down, there's the next page is just blank, and that's because we want to be able to, when you have this physically, to be able to detach this first page and reference it as we enter into some practice, okay? Because here in the next page we have a series of examples in which we're going to use the properties of exponents to simplify each expression. So I'm going to give you all my pointers here with all of these exercises, and we will just go ahead and tackle them in order. So here we go. Here in number 1, I see an instance in which I have an exponential expression raised to a further power. So this looks like the power of a power rule, in which case I will multiply those exponents together. 3 times 5 is 15. My final answer is b to the 15th power. Okay? Cool. So for number 2, I have a quotient raised to a power. So I'm going to use the quotient property in order to have the b and the 4 both individually raised to the 3rd power. I'm distributing that exponent to both of the factors in that quotient. The b to the 3rd power can't be simplified because I don't know the value of b, but 4 to the 3rd power can be. So what's 4 times 4 times 4 give me? I believe it'll be 64, right? Okay, so the rule of thumb is that as long as the numbers are relatively small for the base and the exponent, and they're actually like numerical values, you should strive to simplify it to an actual number. So I wouldn't leave the final answer as having that denominator as 4 to the 3rd power. I would simplify it indeed to a 64, okay? So you may be wondering in certain instances when it's okay to, or appropriate to simplify or not. Just feel free to ask, okay? I can just tell you right away if it's like something that you need to simplify. Okay, so here we're getting to be a little bit more complex. We're just multiplying two quantities together, and one of them has an exponential expression in it, the b to the 6th power. And so what we'll want to do here is, one way that we can think about it is to drop the parentheses all together and recognize that everything, the 3, the b, the 7, and the b to the 6th power, it's all being multiplied together. So we could use the commutativity and associativity of multiplication as an operation to rearrange the factors and then group them by category. So what I'm going to do is put 3 and 7 in a quantity and multiply them together, and I'm going to put the b and the b to the 6th power in its own grouping and multiply them together. Okay, so the numerical stuff, you just multiply. What's 3 times 7? It's 21. No big whoop. Now, for the b variables, and one's being raised to the, we'll want to understand that this single factor of b is raised to the 1st power. That's how we can think about it, and that's probably the most useful way to think about it in terms of using the appropriate rule here. Oops, I made an extra mark I didn't mean to do. There we go. We're going to use the product rule, which is that we're going to add the exponents together. So now the exponent on a single factor of b will be to the 1 plus 6th power. Final answer here will be 21 b to the 7th power. All right, cool. So hopefully that's landing real nice in everybody's brain areas. Great, let's do number 4, which is going to be very similar. I'm going to do a regrouping. All of the numerical stuff is going to go in the front. -5 times a -3. Do a couple of, some grouping symbols and then some parentheses just to hold in this negative factor. Then I'm going to group the p's together, right? I've got p to the 3rd power in the first original grouping, and I'll multiply that by p to the 2nd power. Why do I want to group all the p's together? Well, because in the next step I can use the product rule in order to add the exponents together, and I'll do the same with the q's. I'll do q from this grouping times q to the 5th power in the second grouping. And remember, this q to the one factor of q, I just gave it away, LOL, is actually q to the 1st power, right? So remember that when you are implementing the product rule in the next step. So here we'll get, if it's okay with everybody, I'll just kind of go straight to the final answer because I see it as being something relatively easy to calculate. Also, notice that my two negative factors out in front are going to cancel out their negativity and become a positive factor of 15. So that'll be 15. I'll add these exponents together to get p to the 5th power, and add the 1 and the 5 together to get a q to the 6th power. All right, so it's fine with me for you guys to, do some of these pieces of calculation along the way so long as you're comfortable. But if you want to, show you're working an additional step, that's always a good idea, okay? Great, so let's go ahead and go back up to the top of the page for number 5 and recognize that we have an instance in which we're going to use the quotient rule, but we have a couple of different categories of factors here to deal with, so I would separate them. This is a little bit of trickery that I recommend that you do, is have your 6/9 as its own fraction and separate it from the b's as well, b to the 7th, b to the 4th. So that way you can just implement the quotient rule just on the b's, and then the 6/9 you can just, what's the word I'm looking for? You can just reduce that, right? They have a common factor of 3, leftover factor here being 2, 3 over here, and then here we will reduce this by using the quotient rule. So that'll now be 2/3 times b to the 7 minus 4 power. That's what the quotient rule dictates. And so your final answer will be 2/3 b to the 3rd power, because 7 minus 4 is 3. And you can leave your answer like this with the 2/3 coefficient, or you could let the b to the 3rd power kind of slide into the numerator, and then the final answer could read as 2b to the 3rd power all over 3. That's up to you. That's all about, personal aesthetics with that. I believe your homework, your online homework, will accept it either way. Okay, number 6, we have a -4, a b, and a c collectively raised to the third power. So this is power of a product rule here. So that means the -4 will be raised to the third power. And I want to be very careful about this, letting the -4 be inside some parentheses raised to the third power. I don't need to do that for the b or the c, though, because there's no more negative sign to attribute to any of that stuff. Okay, now -4 to the third power is something that I can calculate. I can rely on what I did earlier with this 4 to the third power. I know that that's supposed to be equal to 64, but if it's negative, then -4 times -4 times -4, which is the expansion of -4 to the third power, will yield -64. And then the b to the third power, c to the third power will just come along for the ride. It looks a little funky. Let's just erase that bit. Try that again just to close up the b. That's better. Okay. And there you have it for number 6. And getting back to the blue color, what do we have for the next bit? Oh, so the next stuff will be 4 to the 0 power. All right, so that 4, right, is anything, and it's being raised to the 0 power, so that'll just give us a 1. Now you may be looking ahead to number 8 and being like, oh, that's also going to be a number 1, because -4 is just any number, and I can raise it to the 0 power and it's a 1. But wait, whenever there's a sign in front of an exponential expression and there's no parentheses to be found, this is how we should think about it, okay? Because this negative sign is not technically part of the base, which is something that's very easy to overlook. So taking the 4 alone to the 0 power indeed yields a 1, but there's a negative sign that needs to come along for the ride. So technically, this last number 8 here has a value of -1. Okay, so you want to be very careful when you're dealing with that 0 exponent, and make sure it's very clear to you what the base is for any exponential expression with a 0 exponent. Okay, and so we're going to continue with this concept in number 9. Okay, recognizing that the only thing being raised to the 0 power is the 3x. The -8 is a factor out in front, so -8 is going to be multiplied by what? What's 3x to the 0 power? Well, 3x to the 0 power is a 1, okay? But you got to multiply it by the -8 that's waiting in the wings, so the final answer here will be a -8. So hopefully everybody's feeling really good about that, understands what we mean. Okay. So last in this set, I believe, yep, is going to be a product raised to a power, and some of the items inside of the product are already exponential expressions. So essentially what we're doing here is we want to take -2, yep, and you want to have that negative inside of some parentheses here and raise it to the 4th power. Then you want to take p to the 2nd power and raise it to the 4th power. So yes, everything is getting a power of 4 on it, but the stuff that's already exponential expressions, you'll need to have a subsequent step in which you implement the power rule by multiplying the powers together in each individual factor. So what's -2 to the 4th power? Well, it'll be -2 times -2 times -2 times -2, which is +16. The p's, multiplying the exponents together, will yield p to the, what's 2 times 4, guys? 8, right? And then the q will have a 3 times 4 exponent on that. That'll be to the 12th power, okay? So remember, when it's a power to a power situation, you are going to be multiplying those exponents together. If exponential expressions are being multiplied with the same base, then you add their exponents together. It's really easy to get those two rules mixed up, okay? Okay, so when you are trying to figure out if you are done simplifying expressions with a non-negative integer exponents, you want to follow a few guidelines, and here is the list of them, and it's got fill in the blank. So number 1, the expression includes no parentheses. If you have any parentheses in your final answer, you have not simplified it enough yet. There's still more work to be done. Parentheses. All right, great. Number 2, each variable or constant appears as a base as few times as possible. So essentially once. So I'll put parenthetically once is the conventional thinking on that one. Number 3, each numerical expression, such as 3 squared, has been calculated and each numerical fraction has been simplified. So we'll just say simplified to kind of be the catch-all for that one. So as 9 in this case. And each exponent is positive. I know we haven't introduced negative exponents yet, but when we do, this is certainly going to transfer over to that. Definitely we want to not have our final answer include any negative exponents. So let's have a few more examples, and then we will get to a few more rules in the next section, section 10.2. All right, so let's go ahead and simplify these again. So not again, we're simplifying them for the first time, but we're just getting a little bit more challenging problems here. So I notice that I have an exponent raised to a product. So this 2 exponent is going to get distributed to the 3, the b to the 4th power, and the c to the 7th power. So in these 2 instances with the parentheses, we're going to implement the power rule, and that means multiplying the exponents. I will do all of that in addition to taking the 3 to the 2nd power to its eventual value of 9, and this will be b to the 8th power and a c to the 14th power. Okay, there we go. A little bit sloppy, but I think you guys get the notion there. All done there. Okay, number 2. We are going to, I would separate, well, okay, so here's what I would actually do first. I would deal with these b's in the numerator first. B to the 3rd power times b to the 5th power is b to the 8th power, because we would use the product rule, which dictates that we add the exponents together. When exponential expressions are multiplied together, they have the same base, and that's definitely what's happening there. I'm going to go ahead and erase that since it seems to be covering up the original problem. And then we still have b to the 8th power in the denominator here. Okay, you could think about this, b to the 8th and b to the 8th, as just, you could straight up, cancel those out if you want, right? And then we can reduce the 14 over 21, and we will get what? Well, there's a common factor of 7, so dividing out the 7 here, we'll be left with a factor of 2 and a factor of 3. So in this particular problem, all of the variable parts happen to cancel out, and we are just left with a fraction of 2/3. And that's that for that particular problem. All right, let's scroll back up for number 3, in which case we have a fraction with a couple of different types of factors. We've got b's, c's, and numerical factors raised to the 4th power. So the numerical factors cannot be reduced. The variable parts don't match in their bases, so the best that we can do is really distribute that 4 over every single factor all throughout this quotient, and then the numerical parts will be able to simplify some more by giving it an actual value. So here we go. It's like the 3 gets a 4th exponent, the b to the 9th power gets a 4th exponent. I'll put that in some parentheses. The 2 gets a 4th exponent, and the c to the 6th power gets a 4th exponent. So anytime you have an exponential expression raised to a further power, we're going to multiply the exponents, and then for the numerical parts, we will just come up with their values. So 3 to the 4th power is 3 times 3 times 3 times 3, which is another way of saying 9 times 9, which is 81. B to the 9 times 4th power is going to be b to the 64th power, or sorry, 36th power, because 9 times 4 is 36. 2 to the 4th power is 2 times 2 times 2 times 2, aka 16. And c to the 6 times 4 power is c to the 24th power. And there's no more simplification to be done there. All right, last one in this section, and then we're going to move on to learning some more exponent rules, okay? So here we go. Let's start by working on this numerator. Let's simplify the numerator stuff, and then we'll be able to use some quotient rule to simplify the b's and c's that come about. So this will be 2 to the 4th power, b to the 5th power raised to the 4th power, and then c raised straight up to the 4th power. Or you could call it c to the 1st power, raised further to the 4th power, but I don't know. You're going to multiply that exponent of 1 times the 4. You might as well just go straight to c to the 4th power. That's fine by me. And then there's still a b to the 9th, c to the 1st power, just a c in the denominator. Now, what do we have here? 2 to the 4th power, as we saw earlier, gives us a 16. This product rule here will be b to the 20th power, and then we have c to the 4th with a b to the 9th c in the denominator. So I would split these up into 3 groups, right? We have 16, sure, and then we have b to the 20 minus 9 power using the quotient rule, and then c to the 4 minus 1 power. Now, why is it a 1? Because remember, any single factor can always be raised to the 1st power, even though it's not explicitly shown to have that, okay? So then, performing the subtraction, we'll have a final answer of 16 to the, with a factor of b to the 11th power, c to the 3rd power. And that's our final answer there. Okay, let's continue this discussion into 10.2, which I have keyed up right here, in which we are going to introduce a couple more exponent rules. Here is b to the negative n power. So, what's the word I'm looking for? Assume n is some non-negative counting number. So if you force a negation on it, so the negative n is definitely, by definition, a negative exponent, you can rewrite it as 1 over b to the n power. So the way that I think about it is, if you see negative exponents in like what I would perceive to be as a numerator space, because this b to the negative n power can be written as over a 1, right? So the b to the negative n, technically, as I like to say, is in a numerator space. You can pluck away the negative sign and throw it in a denominator space. If, alternatively, you have a negative exponent in a denominator space already, you can throw it back upstairs, right, with a positive exponent. So it's like they switch positions by virtue of evaluating the negative exponent. If a negative exponent's in a numerator space, you take away that negative sign and throw it downstairs. If it's already downstairs with the negative exponent, you take away the negative sign and throw it back upstairs. That is the process of evaluating the negative exponent. So, evaluating negative exponents equates to switching its position from either upstairs or downstairs. Equates to switching its position and removing position and removing the negative sign. Hold on. Erase. This description works for me. If you have another way of thinking about it that's slightly different but works for you every time, by all means use that. Okay, let's go ahead and simplify each so that the exponents are positive. So for this first one, we have a 5 to the negative 2 power. You could say it's, in a numerator space, so go ahead and throw it in the denominator space and take away that negative sign. That's what makes these equal. And furthermore, since we have numerical values in our exponential expression, we can always give it an actual value, okay? But we did show some work along the way where we took away the negative sign for the exponent. Okay, let's do a similar thing here for number 2. Now let's throw it upstairs, right, and take away the negative sign. So that'll be 4 to the 3rd power over 1, or just call it 4 to the 3rd power, but then also evaluate it. 4 times 4 times 4 gives us 64. Okay. Cool. Next. Ooh, look at this. We have a negative factor, but don't let that confuse the process with the dealing with this negative exponent. We're going to take this negative exponent b to the 9th power and throw it upstairs, and then that negative 8 is still waiting in the wings, and then what goes down below? Well, there still has to be a 1 down below to, you know, address that space there, to show that it moved upstairs, and then we took away the negative sign. But really, we don't even really need that stuff down there. It's just a mechanism by which we can follow the rule of evaluating the negative exponent, okay? So hopefully that feels good and is helpful as far as like the structure of the work shown. Okay, so for number 4, oops, I'm really bad at accidentally touching the screen with the stylus when I don't want to. Okay, so here we're going to throw this b to the 4th power downstairs, right? Take away the negative sign, throw it downstairs, but who is waiting upstairs? The 6 is waiting. Oh my gosh, my b looks so much like a 6, I have to redo it. Sorry guys, that's supposed to be a lowercase b. So hopefully that is looking like it should. Okay, cool. And be careful when you're dealing with evaluating negative exponents that you're clear on who the base is. Now, 6 and b could have been the entire base if there were parentheses around both of them, but since there are not, only the most immediate item associated with the exponent is going to be the base. So that's just the b. So evaluating the negative exponent has b to the 4th power thrown down in the basement, 6 stays upstairs. Because, I mean, and again, we can think about it this way. If that's at all helpful. Okay, so cool. This item right here is collectively raised to a negative 5 power, so we can put it over a 1, and that can help us, you know, throw it all downstairs, which will be r to the negative 4 power times negative 5, or excuse me. Well, hold on. Actually, if we want to multiply it by a positive 5, we'll throw it downstairs to begin with, and then we have an s, which I need to do like this so it doesn't look like a 5, to the 3rd power, but then raised to the 5th power, which will be positive as long as you throw it downstairs first. Okay, so then we'll have 1 over r to the negative 20th power times s to the 15th power. But wait, make sure that that negative exponent is dealt with, so it needs to, in a manner of speaking, get thrown back upstairs without the negative exponent, which will have us presenting a final answer of r to the 20th power over s to the 15th. Okay. Cool. So if that one felt a little funny, there are other ways that we can do it. So I'll just go ahead and leave that up to you guys to request in class if you need some more or would like some more clarification on that. Well, let's mark this final answer with the boxing and move on to the next thing. Okay, here we go. Yep, more examples. We need more. Okay, so here are 3 more, and then we'll introduce another rule, and then have 4 more examples to finish up this lecture video. Here we go. So I would evaluate these negative exponents. So remember, we're just going to have them switch places, basically. The a to the negative 4th power in the numerator is going to go down to the denominator without its negative exponent, and the c is going to come up to the top without its negative exponent. So here is us just from one step, from the original problem to the first step, just switching the places of the negative exponent variable parts. And then everything else that doesn't have a negative exponent, like the 7, the b to the 9th power, and the 3, they just stay in their current positions, like so. And that's all there is to it. Remember, negative exponents are evaluated by plucking away the negative exponent and switching the position from where it currently lives. So if it lived in the denominator, in evaluating it and taking away the negative sign, you throw it up into the numerator space. So here we go. Let's first take this 4 exponent and give it to every single factor, doing a power of a quotient and power of a product down below as well. And so that'll be b to the 20th, right? Because 5 times 4 is 20. 2 to the 4th power is 16. And then c to the negative 3 times 4 power would be negative 12. Okay, but we need to evaluate this negative exponent here by tossing it up top with the b to the 20th power. 16 is going to stay behind. And we will have b to the 20th power, c to the now positive 12th power, 16 down below. Last one in this set, and then we'll introduce a new rule. All right, this one I would separate into pieces because we have numerical stuff that could be in one ratio, B stuff in another ratio, C stuff in another ratio. So let's go ahead and group them up accordingly. Here's the numericals. Here's the B's. So I'm not even going to evaluate anything in this first step. I'm just going to regroup them. And C's. Okay, let's simplify this first fraction. There seems to be a common factor of 9. It divides the 18 twice. It divides the 27 3 times. And then let's go ahead and quotient rule the B's and the C's. So that'll be 2/3 times b to the, what's a negative 5 minus 3? That'll be negative 8. And c to the negative 4 minus a negative 6. So negative 4 minus a negative 6 is the same as negative 4 plus 6, so that's a positive 2. Okay, so we already have a fraction established here. So the b to the 8th power is going to go down below with the 3. And the c squared is going to stay up top because it has a positive exponent, right? Or just the 2. So hopefully that all feels good and makes sense. But let me know if it doesn't, and we can do more examples, or I can elaborate in class. Okay? Great. Next thing here, last rule of the day. So, rational exponents. And we're only going to really care about the rational exponents of 1/2 and 1/3. They are analogous to something that's already been presented and somewhat familiar to us, and that is radicals. Rational exponents can be redefined as square root of b for the 1/2 exponent, or the cube root of b for the 1/3 exponent. Okay, so basically the root of an exponential expression that has a fraction exponent is the same as the denominator of that fraction exponent. So the fraction exponent being 1/2, the denominator being 2, that's the second root, or the square root, is the analogous form. And then the denominator of this rational exponent being a 3, well, that represents a third root, right, or cube root of the base b. Okay, so let's go ahead and bust out a few examples of these. We're going to start by rewriting it with its root structure. So this 49 to the 1/2 power is also representable as the square root of 49, which we all know is 7, I hope, because you know that 49 is a perfect square number. It can be rewritten as 7 squared. The square root and the square root cancel, and we're left with just a 7. Okay. For number 2 in this set, we have 27 can be cube rooted, certainly, because it's a perfect cube. So the cube root of 27 yields, 3, because it can be rewritten as 3 to the 3rd power. The cube root and the cubing cancel, and we're left with just a 3. Okay, Now let's throw negatives in the mix and make it more complicated because that's so much fun. And this will be the square root, or the cube root. Oh no, actually let's do the negative exponent of it and just throw it down below, right? 27 to the 1/3 power, but you know, throw it in the basement because this is over a 1, right? So switch the positions, and then we'll do 1 over the cube root of 27, which we just established that the cube root of 27 part is a 3, so that'll be 1 over 3 as the final answer there. Okay. And then last example here, the most complicated of them all for the day. Whew, okay, so it's negative, so we just want to make sure that we pull that out in front, and we deal with the negative exponent by throwing the 81 to the 1/2 power in the basement or underneath, right? So this negative sign just comes out to the front. Hopefully that is making sense to everybody here. And then we'll deal with this 81 to the 1/2 power by rewriting it as square root of 81 in the denominator. And lastly, that'll give us a final answer of negative 1 over, what's the square root of 81? It's a 9. Negative 1/9 is the final answer there. Great. So that's pretty much everything we need for to deal with exponents. All the exponents that we're ever going to encounter are, I think these are all of them. And then when we move on, we'll get into some exponential functions, but later on, guys. This concludes the first 2 sections in Unit 5. So enjoy, have fun with that homework, and I'll see you in lecture soon. We'll talk more about this.